and I'm just kind of, until I can basically bleed down all of my savings. So for the last couple of years, I've been getting more into kinetic sculpture. I started doing kind of acousto-kinetic, and then realized just the kinetics themselves were pretty compelling to me. And having a background in physics, let's see if that actually fits with, I just like finalized this movie. There we go. Okay, so having a background in physics, I'm still really interested in kind of natural emergent processes. And so this is an example, for example, of a natural process where, you know, sand goes downhill and it makes actually an amazing kind of pattern just by way of minimizing energy. You know, we're all pretty familiar with that. That's, you know, gravity, wind, rain, whatever. But it's a pretty simple system. So I got kind of interested in, well, if I'm going to centrally drive a process via some mechanism, and I just let things freely move, what's the shape and what's the form of motion that results? So along those lines, so these are kind of like 3 laws that came from a lecture that I'm about to show you, but the main one that I want to focus on is that first point about complex systems and the way they self-organize, and that's really the fundamental aspect of what I'm interested in kinetic art. So hopefully this won't be too loud. Oh, okay, yeah. So to start out, this is a little bit of what I'm working on. So what's underneath this plate is that electro magnet that you just saw, and all the electro magnet does is just turn on and off. And these are just, you know, a safety pin, basically, with some ferrite beads, and the ferrite beads are, I'll even show you. So the ferrite, they're just beads. They have holes in them, you know, and something goes through, and there's north and south, basically. So it'll just want to flip over like that. And so basically, you know, what's the kind of behavior that you get when you constrain certain aspects of a system and leave other aspects to move freely? So this is an example of some things I'm playing around with. Yeah, I mean, and just like he said, you know, we always tend to anthropomorphize. So what is it? Is it a bug? Is it a snake?
It's a virus from outer space and it tries to tell us something.
Yeah. Yeah, so if you have, all these various pieces are going to come into a series of pieces. So if you guys like come up with names, you can yell them out to me of what this should be called.
Ramp up the through.
Okay, so this guy's going to yell at you in an Australian accent, but basically what's happening here is there are, as an example of the way things self-organize, this is really cool. There's a petri dish. No, this is a petri dish. God damn it! This is a petri dish, and there's just a bunch of steel ball bearings. They're only like 1.5 millimeters large, and it's just in castor oil. And then it's under a projection screen, so that's why it's illuminated from the bottom. I think on the outer side he's got it like silvered, so it's conductive. And basically he's got a ground wire connected here, and he's got the hot wire, or whatever you want to call it, kind of suspended above, and it shoots out ions and basically creates a potential of about, what he says, up to 20,000 volts.
Till something spectacular happens.
So he's going to lecture you about this a little bit, which I think is the best way to describe what it is I'm trying to capture.
Making noises, that is a good sign.
So a student is turning up the
Ramp
power.
it up a bit more. Yes, okay, ramp it up a little bit more. Oh, okay, then we have to wait. Okay, so you see that the particles agglomerate to tree-like structures. The trees are self-assembling, so you get self-assembling structures. Stable, like if you break one of those structures, like a small gap here, and then I feed it again with energy, you see it's repairing. with a stable, self-assembling structures. Of course, if you make a big perturbation like this, it does not grow back to the same structure. It grows a different structure. But if you count the number of endpoints, you always get the same number of endpoints. So let me describe that real quick here. So if you get a structure like this, we have three different types of particles. We have the particles at the end which have only one neighbor, like the red ones. And then we have the particles, the trunks, which have two neighbors, like here. These are trunks. And then we have branching points, which have three neighbors. So we classify all particles in the structure into three classes: endpoints, branching points, and the rest. And when you run this experiment, you find that no matter how many ball bearings you have, no matter how much oil, no matter what material the ball bearings are, as long as they're conducting, you always get 22% endpoints and 22% branching points. And the rest makes connections. So this is very reproducible. So this system has some properties which are very reproducible. For instance, that the number of endpoints is always 22%. Another reproducible property is that this system does not form closed loops. Do you see any closed loop in the experiment? Okay, to check that the system indeed avoids closed loops, I make a closed loop. Like this. And then I power it again, and you see it opens up. This system detects closed loop and closed loops. And this is a remarkable reproducible property too. When you look outside and study the branches of a tree or the root system of a plant, you will almost never see closed loops.
Okay, so this is that electromagnet that I was using, and I've just got some magnetic paper over it, and just kind of showing what was powering that plate, and it's going to power some other things I'm going to show you. So basically, it's really subtle. Like, there's not much to it. Actually, it turns out, if you've ever seen like the show from Breaking Bad where they like erase all the data off the. Anybody ever see that? It's actually worth referencing. Okay, well anyway, the point is I was surprised, and I think a lot of people would be surprised to find that electromagnets are not as powerful at a distance as people think. But so this is the power, or this is what's essentially powering a lot of the pieces I'm doing. And then I vary it a little bit in some ways to make it a little bit more chaotic by adding some other pieces of steel and magnets.
What is this magnetic paper?
It's ferro. It's got a little emulsion of ferrous, you know, because they're able to make now nano ferrous particles. So it's just that slap between two, somehow free to move. Very useful to look at what's going on. So these are against those beads, which are ever useful. They're ferrite, by the way, and not neodymium, and that's important to me to point out because it's that neodymium is just too strong. Like, they would just hold together and they wouldn't move against each other because their field is just too much. So this is kind of an example of like, well, what's the behavior? What's the natural pattern that would just happen if things were free to move? So this is kind of an example of that. And so the central part of this thing is the only thing that's magnetic. Like in that electromagnet, this is the only part that turns on and off. And it's not plus or minus, it's on or off. So there's not much to it. And then this outer casing is just metal. So it's a lot of complexity that comes out of a pretty simple source of power. So what happens with this over time, just like sand rolling down a hill or any number of other things, is because these systems like to find a way to minimize their situation amongst each other and their energy, if you don't come up with some clever way to perturb it, over time this will settle into actually a situation where it doesn't move much at all. So that's a part of the engineering around the art of doing something like this. Yeah, so it'll arrange itself actually around the edges of the system, just like gravity take over basically. So these are basically, again, the same magnetic bead with just some pipe cleaner wire wrapped around it, so it keeps them from being too close to each other, so they don't stick together, sort of. It's actually still kind of a challenge to keep them apart. A friend of mine who's here actually named this Electro Muppets, which I thought was great. But actually, the more I work with these, the more I think I'm going to name it microaggressions. Yeah, here they seem to be a little bit more ready to fight. And it's all just because I'm driving them with like a slightly different signal shape. In one case it's more like a sine wave, and in this case it's not. It's a little bit different. Right. So I wanted to point out that there are a lot of efforts underway to model the relationship between shape and gravity and a million other factors and forces via computers. And there's a lot of different software packages to do that. But this one kind of stood out to me just because it was well presented, and I thought it would be interesting to add in to the whole bigger picture of thinking about the interaction of shapes and all the forces around them and how that can change and evolve. And in this case, that's what he's trying to model.
Fitness was based on rewarding individuals for maximizing their net upward movement. For the first 1,300 generations, net upward movement was measured relative to overall body size, producing these very small jumping creatures. These are all from generation 1,300. Beyond generation 1300, absolute net upward movement was used, regardless of body size, and the result was much larger body sizes. These creatures are from generation 12,145.
So anyway, and then this is a piece actually that I showed at the Art on the Moon exhibit up in Seattle. So what it is more magnets. These are neodymium magnets, and then there's two basically stereo channels. It comes off of a stereo amp, but these are inductive coils, and there's a larger magnet in the center. And essentially, these center magnets are driving just by proximity all the magnets around them, and they're just rolling back and forth in a cup, in a dish-shaped mirror. That's kind of what keeps them constantly off balance. And then I've just glued a yarn tail to the ball to give people a better sense of the motion. This was also an interactive piece, but the sensor died on me while I was setting it up. So yeah, so that's the larger one that kind of moves around. And it's just kind of surprising to see how magnets can work on each other at a distance. Like normally with neodymium magnets, you see them snap together and that's kind of the end of the show. So I thought this was a nice way to demonstrate it. What's that?
What were people supposed to be able to do with the interaction?
Well, it was just, I had just had a sensor where they were doing like just distance from the sensor, and that would change the frequency of the signal driving. Yeah. I managed to, this was actually a pretty tricky system to set up. I set it up in a very different form at the last festival, but I really got lucky in finding these polystyrene, I think they're polystyrene, champagne cups at the dollar store, and that made a lot of things possible that weren't before, just for stability issues. And then the last piece that I finished and filmed was this piece called Fire Ants. Basically, it's just giving you a kind of a sense of creature-like existence from inanimate objects. They're just basically two ferrite magnets that are rotating around using a motor, and they're just ferrite beads, some of which are glued via this silicone wire to the glass, and then there's another bead sometimes just really lightly sticking to its neighboring ferrite bead that it just rolls on to give it this kind of animal-like effect. And that's it.